Good to go, Akash?
Yes.
Okay, thank you. Um, so, thanks to the organizers. Looking forward to doing this, spending the next few days with you. I'm just recovering from a bout of something. So if I'm a little low energy, please forgive. If I'm low volume, please don't forgive. Last row. Okay, at least 50% raise their hands, okay. But just keep me honest on this. So we are going to be discussing elastocapillary phenomena of various kinds. So the elasto has to do with a deformable solid of some kind. The capillary says that that deformable solid lives somewhere at the interface of two fluids. In almost everything we will talk about, at least one of these fluids will be a liquid. We're going to be interested in phenomena where, move it right back up, okay. That was back row was supposed to tell me. Okay, better? All right. We'll be looking at circumstances where the solid is deformed, sometimes in a very microscopic way, but that has macroscopic consequences. Sometimes it'll actually be a big deformation in the sense that you might imagine what big means, okay? I'll also try to really stick to the third word in the title. I'm an experimentalist, so I will try to be telling you numbers, phenomena, typical scales, occasionally experimental difficulties. But also, I'm not going to be introducing these topics out of, the force of pure thought. I'll usually be anchoring a concept to some phenomenon. We'll start with some pretty straightforward phenomenon and try to think about what might be the physics driving it. So look, these aren't exotic phenomena. These are things you see, in your everyday life. There's elastocapillary phenomena are super important in the plant world, in the insect world, and in the things you deal with every day. So you might have some intuitive feeling for these things. There are some conceptual traps, though, traps that we have often fallen into in our thinking, and traps that you'll see in the literature that people have fallen into. Very nice work has often fallen into this kind of, some kinds of unusual conceptual difficulties. But there is something intuitive here that you should be able to grab onto. In addition to all of this, there's also in addition to phenomena in the natural world, there's also, I think, more and more interest in this topic because of the fact that we're trying to make smaller and smaller devices. And often now there's a need to make, or there's a push to make devices with softer materials so that they're flexible. These things are very prey to elastocapillary collapse. And as in this case, this is a MEM structure that basically, when the etching fluid was taken away, collapsed. Putting that slide together, and it felt like I should have a gallery of failed experiments in my lab that tell lessons, which is what these people did. So look, elasticity by itself is a very big field. It's an old field and a deep field. I will be very light on sort of tensorial aspects of elasticity. I'll be very light on the beautiful geometry that underlies some of these things. you'll hear probably very elegant versions of this from David Nelson next week. So maybe it's useful to hear the pedestrian version first. So, this is a field that's come back into modern physics in many ways because of the realization that you can deal with geometric nonlinearities in a very nice way. And that's sort of what pulled me into this whole field, the elasto part of it, the large deviation elasto part of it. But that stuff is going to be a sideshow in what I'm talking about today, in the next few days. Capillary physics is also like a very active field of its own. Okay, so we will live at we're not going to go into great depth into either of these, but we'll live at the interface a bit. So, there's people, I don't know, probably in research groups here who do self-assembly, then the non-equilibrium physics of wetting, capillary-driven engineered surfaces that don't wet or want to wet a lot. So that's a field in itself, okay? And we're not obviously going to deal with either of these fields in great depth, but just try and see the bridge between them. So this is roughly what the menu is. I'll try to bring this in more and more detail over the next, at the beginning of each lecture, I'll populate this list a little bit better. Today, mainly we'll tell about capillary things. These may be things that you've seen before, maybe as early as high school, but I'm going to revisit them. Tomorrow, we'll do a little intro to elasticity, and I will go watch Jay Feinberg's lectures, and maybe we can escape. We can have a holiday tomorrow. But that's maybe where we'll start talking about our first set of elastocapillary phenomena. I'll try to make a distinction between two kinds of elastocapillary phenomena, one that comes from the softness of the material, and we'll start talking about that. Then I'll try to make a distinction with materials that aren't necessarily soft, but because of their geometry can bend a lot. And that's what we'll elaborate on the third day if things go well. Okay, but I don't absolutely have to get to the end of this list. So when you need to ask me something, just stop me and slow me down. Okay. All right. Here are some books you can go to read more deeply about the capillarity. This is a gem of a book. It's a book written with a lot of physical intuition, a nice light touch by absolute masters of this game. Elasticity, I don't have the equivalent to offer. This is very nutritious. Take your time and read it. There are reviews. These reviews, a couple of these reviews mix both mechanics as well as something about materials. This is a little bit more focused on interfacial material. So these are places you can go. The focus is largely in those reviews is this type of material softness elastocapillary phenomena. And there isn't something quite right for this yet. Working on that, hope to get it to you sometime. Okay, these are things we won't do, okay? We're going to talk about the simplest elastic solids, Hookean solids, so we're going to not talk about material nonlinearities. We're not going to talk about plasticity for the most part. There will be no gradients in the elasticity. The elasticity will be constant everywhere. There'll be no microstructure. There'll be no, and this is the most boring solid, I promise you. Okay. Similarly, the most boring liquid. There'll be no gradients of the surface, no Marangoni, no time-dependent effects, no viscoelasticity, none of the beautiful liquid crystal kind of things you've been hearing of, and mainly just single component liquids. Finally, this is a field where there's a very interesting subset of work which deals with situations where the line between the liquid and the solid is not so clear. So the liquid can invade the solid can expel fluid back and forth. We won't be talking about those. Finally, almost no dynamics, okay? So you might think that leaves us with very little. That's fine for 3 days, okay? All right. So that's the menu. We start? All right. Any questions, requests? Okay. All right. I'm going to move to the board for a little bit. Actually, I'm going to move to the board for a lot. Stop share, right? Yeah. All right. So you've probably been hearing a lot about surface energies in lecture 1 of J. But the surface energy of any condensed phase has a lower free energy. It owes its existence, in fact, to a lower free energy in the bulk than on the surface. So if you have a chunk of material here, this person would rather be living here than outside. This person would rather be living here than on the interface as well, otherwise the interface would proliferate. So you define the surface energy defined through work needed to create new surface area. Okay. This is some coefficient and the surface area. Okay. And obviously this object has units of energy divided by a length square. Okay. All right. So there is schematically the way people think about this is, or the way it's maybe good to think about is, look, this object coheres, this bulk condensed phase coheres because there are some cohesive interactions between this person and neighbors in the bulk phase. Whereas there's a diminished level of that, maybe there's less coordination around here for this object. Okay. So the typical scale of this is a very schematic way of thinking, but the typical scale of this thing is, some cohesive energy for some microscopic area, okay, surrounding an individual constituent of this thing. I don't know, some U divided by some microscopic, maybe molecular squared. Okay. Now, there's a huge subtlety with defining what the surface is, where the surface is. We're going to start with assuming that there is a surface, and I'm going to draw it as a line. We're going to think continuum. In truth, near the surface, incredibly complex things happen. There's structuration, you can have structuration near the surface. You can have changes in conformation near the surface. It may not be an energy. It may be entropic effects that happen near the surface. The statmech of this has been thought through quite deeply, and we'll take that as a starting point. If you are keen on reading about the statmech of a surface, here's a book. Prepare to spend time, okay? If you want to read that. So the typical scale is something like this, and let's now go look at numbers, okay? And now I will actually share again. Here from that book that I showed you was a few values of the surface tension of common liquids. Okay. So there's liquid helium, there's ethanol, acetone, etc. A bunch of organic common lab solvents, glycerol, water, water at a higher temperature. That's molten glass, mercury, and there's a water-oil interface. The others are water, air, or fluid air. Okay? So this spans a pretty large range of numbers, right? And it reflects the fact that these come from a number of different interactions is where these come from. So these come from all over the place, right? These are, you saw on that list, there are things that are van der Waals, that are weak. Then there's some hydrogen bonded ones, important hydrogen bonded ones. There's some that were transient covalent bonds. There's things that are ionically bonded in there. There were metals in there. And they weren't on that list, but there's also basically things that are entropically held together, like colloidal solids. Okay? So these things go from EV order to KT order. Right? So if we try to put these things together, then let's try to plug in one EV into this. I don't know, what number have I put in here? So one EV, which is and I think I put in A equal to 5 angstroms. I get a number of U is 600 millijoules per meter squared. All right. And if I put in 1 kT, which is 1/40th of an electron volt, I get with this, I get a 40th of that, right? Millijoule per meter squared. Okay. We can go back and look at that table in a moment. All right. Which is, of course, the same thing as millinewton per meter. Okay. I've been writing millijoule. I've been sticking with energy per area for a bit. All right. Let's go back and look at that table. You can see that we are sort of in the right, they give millinewton per. This crude calculation give you some sense of where you should be. All right. In fact, if we look at, this is from, you're not likely to be using molten lava in your lab. You're most likely doing these kinds of experiments with something tamer. So here's maybe a more lab-friendly list of materials from a chemical engineering text. And you can see that this is sort of the range you get to play with easily, at least in the lab. It's not a huge range, and it's all somewhere here. Okay. I'm so sorry. Yeah, this is gamma. Thank you. That's gamma. That's the range you get to play with over here. Easily, at least. So it's important to say that there isn't a huge variation over here in the liquid air values, okay, for the kinds of things that you have lying around in your lab. The next thing is important to say, this is a joint property of both the materials, right? It depends what you see on the other side of the interface, okay, which is why they're careful to say benzenate, toluenate, chloroformate, etc. All right. The next thing I wanted to say is it's important to realize that water is quite high up on this list. Okay. Unsurprising, water has big contribution from hydrogen bonding, okay, which is stronger than all of this stuff. The consequence of this is in your lab, if you start doing this, if you do experiments with water, you have to be extremely clean because almost anything else in the environment will want to displace water at the surface. It'll want to protect the water-air interface. Okay, so it's a tough material to work with, but it's a material that's obviously convenient and important to work with also. Okay, I wanted to say a word about this. Look, you've probably seen this. Work equals gamma times dA plenty of times before. I want to say it's something you should be a little bit, take a moment to realize that it's something a little special, right? It is not what we are used to for a solid. Most of what I've told you for a solid is true for a solid as well. Okay? There is an advantage to being in the bulk of a solid as opposed to the surface of a solid, no question. You do pay energy for creating new surface in a solid, say, for example, by cleaning it or fracturing it. Okay? But if you try to create new surface by deforming it, which is the way we've been thinking about with liquids, if I try to do this, I do create some new surface, but it's overwhelmed by the energy of stretching all the bonds. Yeah, it's overwhelmed by elasticity, typically. Okay, so seeing this in a solid by deforming a solid is a very subtle matter. You do see it if the elasticity of the solid is very weak. You can start seeing effects like this. I have to set the next slide. Yeah, here's some examples of extremely low modulus solids that are made like that and then slowly start rounding. Okay. Here's another thing that was made on a surface. It decided, once it was released from the surface, it decided to slightly distort, pay a little bit of elasticity to minimize the surface area. But you realize this is not what a solid does easily, and it's not a familiar thing for you for a solid. If I cut a small piece of cube of solid out of a big chunk of solid, it is not going to turn into a drop. Okay, it will not bead up for you. And the reason for this is not because there isn't a surface energy, but because the surface energy is fighting against the fact that it's stretching bonds. When I increase the surface area of a liquid, nothing much changes about the surface. New molecules come up to replenish the surface, right? This is not the case with a solid, right? It's those same old molecules now experiencing more strain. It's a different surface now. Okay. We'll talk a little bit more about this, particularly about systems where the surface tension is tweaked or adjusted by putting surfactants or particles at the surface. But by and large, let's now think of just pure bulk liquids, okay? All right. Any thoughts, questions, any troubles? Okay, good. All right, now let's think about surface tension in a slightly different way. Again, maybe this is something you've seen before, but I'm not doing one of these terrible magnetism problems that you've been subjected to at some point in your life, but I'm not going to put a magnetic field over here. But let's say I have a fluid film here. Okay. This object is a rigid frame, and this is a slider. All right. Now, if I were to pull this object this way, apply a force, I increase the surface area in that way, then I do work on the slider, which is gamma times the increase in, let's say this length is L, and I move this distance dx, it's the new area, right? Right? To account well, I should probably take into the fact that this is two surfaces. Let me put a 2 there. All right. So here, the interpretation, of course, is that this is like a force per unit length, right? So hence it's the force per line is the interpretation, and hence the word surface tension. Okay, and that's maybe a comfortable, familiar way to think about things as well. All right. So I think the important thing to see is that for a liquid, this tension is always a tension, and it's always isotropic. And for the kinds of liquids I've talked about before, where the bulk is like the interior, it's always the same number. You can do this experiment and nothing's going to change as a function of how far you pull it. For a solid, of course, it can support all kinds of anisotropic stresses. Okay, and so that's not the case. Okay, so now let's think a minute about this one. How about if I had my slider there? And what's going to happen? I'm seeing sort of micro movements of people's heads and hands, and you can say something, it's okay to be. Is anything going to happen to this? The move left, right? Neither way? Say something, you're making me very nervous now. Say a word, say a name, say a... The question is anything going to happen to this? Or is this a perfectly happy static configuration? Same liquid. Nothing's going to happen, right? Perfectly happy static configuration. If I burst this film, what's going to happen? Huh? It's going to move to the left. How far? Okay. So the one point was maybe it's got something to do with the amount of energy I release when I burst it. Okay, so you're saying the answer is going to be different if I burst it and then let my hand go, or if I burst it and then do that. Okay, in your way of thinking, if I break the interface while holding this static and then take my hands off, I'm going to get a different answer because I'd have sort of absorbed the energy that I got from with my hands of bursting that interface. So I promised you nothing dynamical. Okay, this thing will, I think, as most of you are saying, move all the way to the left. This thing wants as little area as possible. Okay, it's not like a solid, it has no natural length, it wants to go all the way to the left. All right. I thought I would bring something to show, but I didn't have my act together completely. Let me try to show you a version of this that we did. So here's a loop. Okay, this is not exactly that, but in cartoon version, it's that. Okay, and we're going to burst we're going to burst the thing. Oh, I'm sharing, yeah. Going to burst the thing in the middle, I think. That's odd, it was playing. Oh, that's too bad. Okay, I'll try to show it to you tomorrow, but we were trying to do, a rough version of this much nicer thing that we saw. Okay. So you burst that intermediate thing. This thing will expand as fast as it can. Okay. It'll push back. There's no constraint, it'll go. And it doesn't matter. It's not being driven by any energy you recover from here. It's just that it wants to be at zero, as minimal surface area as it can occupy. Okay. 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 So now let's think through a few consequences of what a minimal area means. Of wanting to occupy a minimal area means. And, in the case of a small drop of fluid, area minimization means it wants to become an absolute sphere. We'll talk in a few minutes about what small means. All right. But for now, let's just think about just area minimization. Okay. So let's start with minimizing the area of a surface. Okay, so I don't know, here's a surface that's, it's curving in. Okay. And the only thing I'm really going to impose on this is, on this object is maybe some boundary conditions. This film is going to be held somewhere. Okay. So what I'm trying to do is I'm trying to minimize this area. So this is something like this. Okay. I will leave you to figure out. You're okay with area? I'll leave you to figure out area in your favorite way. You use Jacobians or whatever you like. But this is the area of the surface where, sorry, by hx, I mean, okay. So there's no constraints on this except maybe some boundary. All right. Now, if you minimize this, you get the Euler-Lagrange equation that looks like this ugly mess. Okay. All right. The ugly mess for small slopes is not such an ugly mess. It's just Laplace equation. In small slope. Okay. This is just. Okay. Yeah, for small values of slope. It's good? Okay. I want to think about this in a slightly different way. I want to show you that this is actually can be written slightly differently. And the slightly differently is that this is just equivalent to divergence of the normal on the surface equals 0. And maybe this is transparent to the theory type people amongst you, but maybe I will labor through it for people like me. So here's the surface. Say if you have a surface you have a surface like this, okay? Then the normal points along this, okay? So here, fxyz is, in the way I've written it, it's h of xy minus z equal to 0, right? Okay. And if you normalize this, you'll see that you get exactly that this is along the normals. Okay. All right. So it's a surface along which the divergence of the normals is 0, but it's also so far we've just said this thing wants to have minimal surface area. It's useful to think of it in terms of curvature also. So let me try getting to that as well. We'll erase our slider. Okay. And instead of a surface, I'm just going to deal with a plane curve. Okay. So imagine we're just dealing with a plane curve, which is, something that looks like that. Okay, this is just h of x. All right. So here is a tangent to the curve at some point, and here's a tangent to the curve, at some distance along this curve. Okay, ds. All right. And the tangent is rotated by some amount by the time you get here. This rotation of the tangent is there, okay? And that defines the curvature, right? So the ds is just 1 plus hx squared dx, right? So the curvature of this object is just the rate of rotation of the tangent. Which is d phi ds. And you should go check that I've done this right. This is just hxx over root of 1 plus hx. No, not this. Okay. Which is exactly what we had in there. Okay. Actually, you should check that this is the same as this. So it's for a plane curve, this is also actually just a rotation of the normal, right? The tangent has rotated by phi. The normal is also rotated by phi, right? So for an actual surface, as opposed to a curve, there's also rotation in the other direction, right? You can get along this axis and then along the y-axis. You should also add another term for that. So what you should see is that these are the curvatures in two orthogonal directions. So this says that the sum of the curvature in two orthogonal directions is 0. Okay. Now, it's a result which I won't try to get at, that the sum of the curvature in two orthogonal directions doesn't depend on the orthogonal directions you picked. So if I decide that this is the x-axis and that's the y-axis. And I attached this to this curved object and I tried to find the curvature along one direction and the other direction and add them up. Then it doesn't matter what choice of axis I made. I could have picked any directions so the curvatures in two orthogonal directions is an invariant. That's called the mean curvature. So this thing is a statement that the stuff we wrote means that these are mean curvature of a surface is 0. Okay. That means there are infinite number of pretty pictures of this. So let me show you some of them. Okay, so just pictorially, here are, here's a surface. Here are two orthogonal directions. You add the curvatures along these directions, and you get, something that doesn't depend on your choices. Here they've picked the direction of maximum and minimum curvature. So these add up to a fixed number. Okay. There's another combination you can make out of the maximum and minimum, the two orthogonal curvatures, which is the Gaussian curvature. Maybe we'll come back to this object in day 3. Okay. So you can solve for minimum curvature things. These are the things that you may have seen. You dip objects in soap films and you ask what shapes you get. These are all zero mean curvature shapes. This, for example, zero mean curvature doesn't mean flat, right? It just means that if you have a positive curvature in one direction, then you have a negative curvature in the opposite direction, and that allows you to get away with this shape, catenoid. This is a 150-year-old high school experiment. There's many more of these, but that's what the statement says. Okay, now where does that leave us with our drop? What's the mean curvature of a drop? Okay. Where did we? Okay. What's the mean curvature of a sphere of radius r? Have a mic, grab a mic.
And while you rub that board, I'm just going to make a quick announcement, which is completely unrelated to your talk.
Yeah, please.
So there's been a change in the poster talk. So just check your emails. So so Anupama has created a Google Drive folder. Okay, so please upload it there. Don't need to email it.
So what's the mean curvature of this object? So you look at a point on the surface here, and you take the curvature this way, 1 over r. And then you take the curvature in this direction, and that's 1 over r. And that's, if I want to really take the mean, by the way, this object is often given the name h. This is 1 over r. So what happened? That's a problem, no? Okay. Okay. Yes.
In this 2D experiment where you are removing fluid and then it is minimizing the area. So does the outer fluid has to be compressible for that, or I mean, how does in 2D, how does that happen? That volume is decreasing?
There's no outer fluid, it's just air, no?
In
Oh.
that experiment where you have both sides.
Okay, good. I think you're coming to the heart of why we're in trouble. Good. Okay, this is the way I think about it. What I'm going to tell you immediately now is we did area minimization with no constraints except you must attach to a boundary. Okay? The big difference here is I took a little piece of fluid outside bulk fluid, and I'm going to ask you now what its shape is. I must conserve volume. Okay? When I conserve volume, that's an additional constraint which is not in there. The way I think about those experiments is there's absolutely no volume constraint. I dip some frame into this, and I pull out an amount of fluid that is allowed to self-regulate. It'll drip till it can do one of these shapes. Okay? I'm going to show you that immediately now, if we add volume constraint, life changes. Okay. Yes, please. Right now, there's no gravity. I hope in 10 minutes, we'll say when we can totally ignore gravity. Okay. Right. If all we are doing is surface area minimization with no other constraints, then you're stuck. Okay. But now there is a constraint, and it's actually it's volume. You need to specify this volume in here, right? So really, the kinds of thing you will end up working with is the energy is gamma times the surface area of the object. And then, there's some Lagrange multiplier. This Lagrange multiplier has the name pressure, which says that the volume must be equal to the original volume of liquid that you were given. All right? So V0 is the original, specified volume. And if you want to figure out what this Lagrange multiplier is, then you just do this. Just minimize, just assuming it's a sphere, right? So let's just say that's R. So I'm just going to do, I'm going to do MV is 4/3 by R cubed, which says that if I take these together, I get A is 4 by 3V over 5. Okay, you do the tedious algebra. You just not so tedious algebra. You extremize. Yeah, you extremize with respect to this, and you'll find that the Lagrange multiplier is 2 gamma over R, okay, or 2 gamma H. Okay, this pressure is called the Laplace pressure. Yeah, we'll do some numbers now. So I'm going to use gamma equal to an incredibly clean water against air. And if I pick a diameter of 1 millimeter, I get a pressure of 288 Pascal, which is about 0.003 atmospheres. this is not nothing. Huh? I mean, it's small, but I don't know. Do any of you work with very soft materials? This is not an unachievable elastic modulus. There can be materials as soft as this. I'm not sure what your jello was, but quite a bit. Okay, but when you're at 1 micrometer, well, this is 3 atmospheres already. Okay? So these can be very large pressures. Okay? And that has nice consequences sometimes. How am I doing on time? Okay, look, let me, you can think about this whole thing in a different mechanical way. I'll just sketch it, but I'll leave you to work it out. Maybe I'll try and write notes, which may or may not be more organized than what I've got on the board. But you can think about this in a different way. You can think about this just mechanically. Try and draw, free body diagram with this kind of box as your Newtonian volume. Say the pressure inside is P in, the pressure outside is P out. Okay. Then on the sides of this box, you'll get no contribution. You'll find you have an unbalanced force on this object, and that's supplied by the tension along that equator. Okay, and you should try this. You should get the same answer. All right. Okay. Maybe the small additional thing to say also is that you can think about this locally as well. So if you have a flat surface, okay, and you say, I make a bump over here. Bump won't live very long, but you can ask what the local change in pressure is needed for that bump to exist. Okay, and you can take the local curvature. Gamma times the local mean curvature will give you the value of pressure at that moment. Okay. Let's think about gravity now. All right, that's been at the edge of our minds, right? I'm going to erase that stuff now. Any thoughts, any questions, any things to say? By the way, how many of you work on capillary kind of things? Show your hand. I don't need to grab for the mic. Okay. And how many of you work on things that you think of as elasticity? Okay. Let's see. Just as a poll, how many of you are experimentalists? Oh, okay. Good. All right. No, I have nothing against you. Nothing against the rest of you. Okay. Okay. Let's do a simple way of introducing gravity into a problem. At the same time, yes, please. Sorry, this is the drop. It's a drop. Volume of the drop. Yeah, this full volume of the drop. Okay? Thanks. We'll now start putting not just gravity, but let's put a solid in there as well. All right? Okay. Let's think about this fairly everyday phenomenon of capillary rise. Okay. Okay. Everyone sort of knows what I'm talking about already, right? All right. Except let's not do it in three-dimensional situation. Let's do it in something simpler and two-dimensional. Okay. I'd like to think about this situation where I have two maybe parallel objects, two plates. Oh boy, that went wrong very fast, didn't it? I've got some Escher drawing over here. So I have a pool of fluid and I get capillary rise in this. And this allows me to think just simpler, This is just a two-dimensional version of the same thing. All right. So, I mean, the first thing to ask is, where does the fluid rise at all? Right? It's increasing. It looks like increased fluid surface area. Huh? But I mean, a second look tells you, look, it's rising because something about the solid surface is being reduced, and maybe that's advantageous. All right. So let's take a look at that. Okay. So let's say this height is L. What's the other parameters I might need to specify this problem? Obviously, the distance between these two things. Thank you. Okay. And let's say this is long enough that it doesn't matter. Okay. So this is width. Okay. So the energy of the state per width, okay, is now it is the liquid solid gamma between liquid and solid, okay, which is now, there's a big liquid solid interface times length. And I have taken away a gamma solid vapor. There used to be a gamma solid vapor, which is now replaced, again, times L. What I've paid for is gravity, right? I've taken, I don't know, rho G, rho G L D sort of is the area times the width. Everything is per width. And I've raised it by a height L over 2. All right? It's good? All right. So if I extremize, I get this height is delta gamma divided by rho G D. And delta gamma here is gamma SV minus gamma LS. All right. So please notice that this better be positive. The liquid must, the solid must prefer the liquid next to it than vapor. All right. And it only enters as delta gamma, not independently as both of them. Okay. Yes, please. I'm trying to estimate the potential energy of this bunch of stuff over here. Okay, so I've done the crude thing of saying the center of mass is at L over 2, and I've multiplied by the volume. Okay, this is just mgh, and my h there was L over 2. Thanks. Okay. There is no gamma LV in this picture. One small thing to note is we'll see this character again, with this combination of characters again. And it's useful to note that surface tension divided by rho g has dimensions of L squared. This thing has units, or L squared, right? Length squared. Okay. It's good, straightforward. You should try to work out the tube yourself because I'm too lazy to do this. The answer is very similar. You're going to get a factor of 2, and you're going to get the radius of the capillary tube. You should try putting in numbers for this. For example, you should try putting in maybe, I don't know, put in 10 micrometers for like the xylem of a plant and see how much a tree can get just by passive capillary action. It's more complicated there, right? Because there's loss of fluid from the top. You're pumping fluid a little bit by evaporation, but you'll find, at least for me, the numbers are quite remarkable. Okay, so try putting in 10 micrometers and whatever you can find about delta gamma. Imagine it's of the same order as all the other numbers we've been dealing with, right? And see what you get. And that's a useful thing to do. Okay, but we forgot, we didn't deal with this shape. There's something nice over there, and that something nice over there may have told you that that's sort of the reason that, you know, it does want to climb the surface in the first place, right? The fact that it's tending to wet the solid. So let's look at that. All right. Just to make life simple for us, let's look at it again in this 1D geometry. But let's just keep one wall, just to be kind to ourselves. What did I do with the red? That was my color for a solid. Okay. Suppose we have the wall. Okay. And suppose we did that. Suppose that's our wall, and we want to look at the shape of this object. Okay. How should we deal with that? Now, we already actually have the technology in place from a little while ago. And that's the following. Okay. Here, outside here is, let's say, atmospheric pressure. Inside here is some pressure, which could depend on position now. You already have a sense that it's going to depend because this thing is, the curvature is changing, right? Pressure over here is what? What would the pressure out here be? It's the same as the outside pressure. Yeah, whereas it's clearly not there. Otherwise, it wouldn't be able to sustain that curve by what we've looked at so far. Okay, so let's say we start off with an H naught here. And we use exactly what we've done so far. So this is something that does this, right? H is some H naught. Yeah, is some H of xy. All right. The relevant surface tension here now is gamma LV. right? Because it's the fluid, sorry, liquid to vapor. I should have said this a little bit more clearly earlier. This doesn't need to be liquid and vapor. It could be two different immiscible liquids. Okay, but I've been using LV as shorthand for one liquid and something else. Okay, this times the curvature is the difference in pressure. So now we know the technology for this. This is gamma LV times HXX divided by, square root of 1 plus HX squared is rho GH. Yeah. In small slope, this is just easy to deal with. It's just HXX is in small slope. It's just rho G over gamma LV H. All right. And you can either solve this, or you can just solve it by scale. You can see that this is going to be some H naught over some length squared is H naught times this combination. All right. So this is going to be this is just going to be over some length, and that length is square root of gamma LV over rho G. Which is, this object is called the capillary length. And this is the scale at which we will define small in terms of gravity. All right. So if you put in numbers for air-water interface, air-water, LC ends up being something like 2.7 millimeter. All right. So anything much smaller than that, you can forget about gravity. Anything bigger than that will not be a sphere, because then you should do that extremization again with gravity added. Okay, gravitational potential energy should be thrown into that, and then you will get a shape. So the shape of this for small slope is an exponential, and the exponential is governed just by gamma LV. Okay, you can add that back in here a little bit if you want to. If you want to do a more refined version of this, you can add that back in. Okay, but it doesn't make a big difference. You're comparing this against a surface that used to be flat. That's it. So it's a small correction. Yeah. Okay. So now that we have a sense of what small is, we'll do a little bit more of contact with a solid. Okay. Anything you want to talk about before? Yes.
This height doesn't depend on gamma LS. Gamma LS, so sort of interfacial density between liquid and solid. So H naught should depend on that also. Right?
Okay, good point. Okay, I haven't told you what H naught depends on, right? Very nice. So H naught has sort of quietly vanished in this picture. There is a penalty to the value of H naught. And what's hidden under this picture is that actually when you do an experiment like this, things tend to stick. So if I put a glass slide in and I pull it up a little bit, things will often pin. Okay. If you ask what the equilibrium value of this is, then if you ask me what H naught should be, then you're absolutely right. I'll have to put back in all this solid surface energies as well. I have pushed that under the carpet because H naught happily cancelled over here. Yeah, good. Okay. One more collision between a solid and a liquid. All right. Again, this is going to look familiar, and I hope it is. I'm going to show now the contact of A. A drop on a solid, and it's an old classic problem. But I want to tell one or two useful lessons that I learned from looking at it. Okay. And also because it sets up what we're trying to do next. So for the next little while, we're going to talk about this situation where we have a solid substrate. And I have, this is an absolutely rigid solid. Okay. And I want to deposit a drop of volume V0, a small drop. And now we know what small means. Small drop means V0 is much less than LC cubed. Yeah. And I want to put it on this, and you're going to get a drop shape that looks like this. And the question is, what is the shape of this drop? That looks ridiculous. You can't get such a. I'm going to make look a little bit more compatible with each other. All that. Okay. So now the question is, what is the shape? And this is an old thing, and it's depending on where you're from. I think this goes by the name of Young and Laplace and Dupre. Contact. This, all right. So what do I get out of small? I get out of small the fact that there should be no hydrostatic pressure variation in this. Okay? Gravity doesn't enter now. I can treat the pressure in here as uniform. If I treat the pressure in here as uniform, what can I say about the overall shape of this object? It's got to have the same curvature. It's got to have a uniform curvature. It must be part of a sphere. Okay? Yeah, so this is a cap of a sphere. So this is, so the shape is spherical cap. Okay. I don't know, I could specify this problem in one of two ways. I could either tell you what that angle is, ask what that angle is, or ask what this radius is, and I know the volume and I'm done. Right? Good. So the unknown is A or theta. And the constraint is that V cap equals V naught. Okay. I'm using cap to say this, the volume of the spherical cap, okay? So I'm asking now for the change in surface energy between this situation and the situation of a clean surface and a drop somewhere else. All right. So the change in surface energy is now pi a squared times gamma SL minus gamma SV, right? There's a solid liquid interface now. Okay, I'm going to label this liquid. This is the solid. This is the vapor. Again, this could have been another liquid, but I'm going to use V, right? There is a pi a squared times gamma SL now, which replaces an empty space here, which used to be pi a squared minus gamma SV. We're okay with this? Yeah. Plus the area of the cap times gamma LV minus 4 pi r squared times gamma LV, which is the original surface area of this object. Okay. Now, V cap equal to V0 is a constraint. And then, you can go look up algebraic expressions that show you what V cap are. V cap is some function of A and theta. A cap is some other function of A and theta. And you can minimize with this constraint on one variable. Let's say we minimize on theta. The answer you get is delta gamma, same old delta gamma, is gamma LV times cosine of this angle. Okay. So in general, this is called the contact angle. And in this particular case, it's called the Young-Laplace-Dupre angle. Okay. The angle you get by full energy minimization. All right. You can think about this a little bit from a force perspective. Okay. Or it's common to do this. You may have seen pictures that look like this. S gamma SV theta. Yeah. You should, of course, please understand that these aren't vectorial quantities. And these always come from an energy minimization. If those arrows are there for anything, they shouldn't be representing forces, but directions in which displacement happens to produce the work done by these interfacial areas, okay? But this looks a lot like horizontal force balance, okay? Looks like force balance in horizontal plane. Okay. So there's a few points to be made about that. I wanted to say again that there is no independent variation with these two things. It's always the difference. If you think you can back out from an experiment like this, either of these values independently, there's something you should worry about. The second thing is, you can put stresses on the solid. Say you put the solid under tension. All right. I don't know. Say you put a stress here and you put a stress here. Won't make a difference. Okay, these will cancel. So it will not be possible to back out things about these two, about something like this using an experiment, a contact angle measurement. Okay. And that's I think that's an important lesson from the simple drop to carry, okay? That it doesn't depend. If you do full minimization, if everything is equilibrium, then it shouldn't depend on the state of stress in the solid. Except to the extent that if you stress the solid a lot, then you will modify the surface energies of the solids, but those are fancier effects, okay? Okay, so the obvious question is, look, we have what looks like horizontal force balance. What's happening with vertical force balance? I made a little bit of a dance about how we shouldn't think of these as forces, we shouldn't think of these as vectors, but rather directions along which contact lines can move and projections of areas along those directions. I didn't really allow it the chance to move. The way the problem was formulated, I didn't really allow it the chance for the contact line to move vertically. Right? I didn't say the contact line is allowed to go out of plane. And that, that was a separate statement from saying that this is a spherical cap. Spherical cap relied on other things. It relied on the fact that this is a small drop, okay, and much smaller than LC in scale. But it didn't say anything about what goes on here. So the presumption here is that if you want to think about it in force point of view, the presumption here is that this is a rigid solid, and I put this in as a constraint that this object can provide as much restoring force as you need in order to keep the surface immobile. I can tug as much as I want, and I said rigid from the beginning. So I put things in as a constraint. Okay. Where we're going to head to is places where you think this might not be a constraint. And that's going to be the first sort of elastocapillary thing that we'll talk about tomorrow. Okay. But before we do that, maybe I'll just quickly sketch what you do as a contrast. We should quickly do liquid substrate, which can provide which will provide only a desire to minimize surface area and not want to provide any static forces here. So let's look at this. This is the other famous classical situation. So this is the Neumann contact. This is this guy, and here's another immiscible liquid. Okay, so this is liquid 2, and let's say this is liquid 1, and let's call that vapor as usual. Okay, you get something that looks like this. This guy is, again, it's a minimization problem. I don't know, let's split this into two pieces. Now there are, it's different. This eagly shaped object doesn't have the same contact angles above and below the plane. Okay, so this guy is, I don't know. There's two different angles here. I just want to be consistent with what I've been writing. Beta and alpha. And again, if these are small, both are spherical caps, but they're different spherical caps with the same perimeter but different contact angles. Okay, so the liquid gets shared above and below the surface differently, and you have to take V1 A alpha plus V2 A beta minimized with respect to alpha and beta. And you'll get things that look, again, you'll get things that look a lot like horizontal and vertical force balance. You'll get beta, alpha. You'll get things that look like gamma, LV. Did I pick liquids? Yes, I picked liquids. Okay. Maybe I won't write these out explicitly. I'll put these for you in the notes rather than going through this. But what you'll get is this component, gamma L2V cos beta, gamma L2 L1 cos alpha will add up to gamma L1V. And you'll get what looks like vertical force balance also. All right. The point here, I mean, the big point of distinction, these look like maths problems, but here there's no, I can't add arbitrary forces in the horizontal plane. There's no way for me to do this. First of all, I will break horizontal, quote unquote, horizontal force balance if I do that. Secondly, there's no way to do this in a liquid. There is only one value that I can have for a bulk liquid of this force. It's not like a solid where I can add a stress to the underlying solid. There is a unique value of gamma L1V, and I can't. The thing I did of adding in orange stresses here, can't do it. Okay. So I think that's going to be a big distinction. But where we're now headed to is we're going to think about this when we start off, which is here. This is soft, solid, and on this side, and we understand what's going to happen when the drop of liquid comes in. It's going to have a spherical cap if it's small, but then we have to figure out some things about what's going on here. And that's where we'll start tomorrow. But I just wanted some quick sense. How are we with elasticity? What do we need to say? Everyone knows what a Young's modulus is and a Poisson ratio is? Everyone is okay with a bulk modulus and a shear modulus? You could go from one way of thinking about it to the other way of thinking about it. Okay, maybe don't be shy. Okay, I'm hearing pretty confident yeses on the first way of thinking about things. I'm hearing less. I'm hearing more murmurings about the second way of doing things. So maybe we'll spend like a few minutes on that and move on. Is that okay? But really, we've done sort of liquid solid, liquid rigid solid, liquid liquid. But this is where our first elastocapillary phenomenon will be contact of a liquid on a soft solid. Okay. Okay. See you tomorrow.
Yeah, let's thank Professor Menon, and maybe we can take one or two questions if anyone has any.
Okay. Thank you. I have some interest in understanding how a solid grows over a solid. So there the problem is because of the facetting. How to treat the facetting of the droplet when the droplet is solid. So it's like a heterogeneous nucleation. So there is one surface which is, let's say, solid A, and then another solid B, which is growing over the surface, but it's solid. So we cannot take a spherical cap or something because it's a solid, so it would have some facetting. And I don't know how to treat that.
I think I'd have to hear a lot more about it to have anything like a response, but I'm happy to chat about this.
Is there any more questions? Okay, so there are some few announcements then. So first of all, let's thank Professor Menon again. And